Physics Investigatory Project. How physics is helping to fight COVID-19. Here we'll discuss about the physics of COVID-19 transmission, how physics is helping prevent COVID-19 through infrared thermometers, oximeters, and N95 masks, how physics is helping COVID-19 patients through X-ray crystallography, cryo-electron microscopy, CT scans, and ventilators, and lastly, the conclusion, presented by Anish Parthasarathy, Aryan, Skandan, and Srivathshan. Now for the index. Here are the contents that we'll discuss. Aim, basic knowledge, purpose, N95 mask, infrared thermometer, oximeter, X-ray crystallography, cryo-electron microscopy, CT scans, and ventilators. Conclusion and the bibliography. Aim. Today's times are difficult and challenging. This pandemic situation has changed our habits, our lifestyle, and our life completely. While we are praying for everything to become normal again, we will look at few instruments which has helped us to fight COVID-19 and the physics used behind those instruments. We will discuss in detail about N95 masks, infrared thermometers, pulse oximeters. We will also go through the physics of X-ray crystallography, cryo-electron microscopy, CT scans, and ventilators. Basic knowledge. Understanding the physics of coronavirus transmission. This can help us be better prepared to tackle disease outbreak in the future. When physicists say that there is physics in everything, they mean literally everything, including how a disease is transmitted, from the generation of virus-laden respiratory droplets to dispersing in the air to inhalation or deposition on surfaces. A team from Johns Hopkins University in the US tried to decode the flow physics of coronavirus transmission. The paper published in the Journal of Fluid Mechanics notes that this can help us be better prepared to tackle disease outbreak in the future. The paper also lists preventive measures such as use of face masks, hand washing, ventilation of indoor environments, and social distancing. The fluid dynamic analysis help to understand the mechanisms behind how the droplets are generated in the respiratory tract and also characterize the density, size, and velocity of ejected droplets. The team also tried to estimate the settling distance, evaporation time, and transport of the particles. They also looked at the effect of external factors such as air currents, temperature, and humidity. Previous studies have shown that a single sneeze can generate thousands of droplets with velocities above 20 meters per second, whereas coughing generates 10 to 100 times fewer droplets than sneezing, with velocities of approximately 10 meters per second. Breathing and talking generate jet velocities less than 5 meters per second. Taking all this into consideration, the paper notes that this is why a 3 to 6 feet social distancing guideline is issued. The final stage of airborne transmission is the inhalation of the virus-laden particles and its deposition in the respiratory mucosa. Face masks provide inward protection by filtering these particles. Masks also provide outward protection by trapping the virus-laden droplets expelled by an infected person. Purpose. We have undertaken this project how physics is helping to fight the pandemic because we can explore new avenues of physics during the course of the project. We can get a deep knowledge on how various instruments used during the pandemic are based on some integral principles of physics. We can understand the major role of physics during the pandemic.
Hello, my name is Aryan, and this is for the Physics Investigatory Project, and I would be talking about how physics is used in N95 masks. It's 2022, and by now we've all been wearing N95 masks for nearly about 2 years, and we've learned a lot about them. But do you know what makes the priced N95 mask so special? The electric charges. The fibers in regular cloth or paper face masks filter out particles by physically blocking them. But the fibers in an N95 mask also use a great physics trick. The fibers are electrically charged. Electric charge is one of the most fundamental properties of all particles. Just about everything around you is made of three particles: the proton, the electron, and the neutron. For now, let's ignore muons and neutrinos, but fundamental particles that actually exist, as well as other particles that are theoretically possible. Just as every particle has a mass, it also has a charge. The proton has a positive electric charge with a value of 1.6 into 10 power minus 19 coulomb. The unit for measuring electric charge, the electron has the exact opposite charge, that leaves the neutron with zero charge. Now let's know how the N95 masks actually work. Now imagine something similar to the electrically charged pen and water, but at a small and a much smaller scale. Instead of a pen, you have a bunch of plastic fibers. Instead of the water, you have the drops that fly out of someone's mouth. This is essentially what happens in an N95 mask. The fibers in the mask attracts those drops, keeping the wearer from inhaling them. At a very small scale, things tend to stick together due to what's called the van der Waals force interaction. This is basically an attractive interaction between two uncharged objects because of very slight charge separations. With an N95 fibers, you don't have to rub it with some other material to get it charged. The fibers in the masks are created from an electret material. This word comes from the combining electric and magnet. No, it's not an electromagnet. It is a permanently electrically charged object, just in the way that a bar magnet on your fridge is. There are a couple of ways to make electret materials. One is to bombard the stuff with electrons so that they get stuck in the fiber to make it stay charged. The other method is to heat up a material in an electric field. The increase in temperature allows the molecules in the material to rotate into a polarized state. Due to their interaction with the electric field, once the material cools off, the molecules stay polarized. This makes a slightly different electret material. In that, it creates an electric effect even though it's still neutrally charged. So the electret fibers in an N95 mask not only block small particles by getting in the way, they can also attract them with the electric interaction. So they get stuck to the fibers. This means that those water droplets carrying a virus don't get inhaled, and the mask wearer won't be infected. Of course, an N95 mask also blocks other small particles like dust, paint, and other toxic stuff that might not be great for a person to inhale into their body. But it cannot block medium-sized particles as they are pushed by the surrounding air, nor not hitting any fibers. Since N95 mask can also block about 95% of medium-sized particles, therefore it is called as N95 mask.
This isn't at all like a strainer, because N95s are much cleverer than strainers. The overarching goal of an N95 mask is instead to get an airborne particle to touch a fiber in the mask. Regardless of how big an airborne particle is, once it touches a fiber, it stays stuck to it and doesn't become airborne again. This isn't anything special about the fibers, but about the size of the particles. At a microscopic scale, everything is sticky, because the weakly attractive force between molecules is more than strong enough to hold very, very small things in place. So you shouldn't think of N95 masks like a fine window screen that keeps insects of a certain size out. You should think of them more like a sticky spider web that can catch an insect of any size as long as it touches a strand. And so N95 masks use a bunch of different clever physics and mechanical tricks to get particles to touch their fibers. First, many spider webs are better than one. Unlike strainers, where stacking many identical ones doesn't improve the filtering at all, more layers of sticky fibers means more chances for particles to get stuck. And how likely particles are to hit or miss a fiber depends in large part on their size. Airborne particles larger than 1/1000th of a millimeter basically travel in straight lines because of their inertia. And because there are so many layers of fibers, their straight line paths are essentially guaranteed to hit a fiber and stick. Airborne particles that are really, really small are so light that collisions with air molecules literally bounce them around, so they move in a random zigzag pattern known as Brownian motion. This zigzagging also makes it super likely that a particle will bump into a fiber and get stuck. Particles of in-between sizes are the hardest to filter. That's because they don't travel in straight lines, and they also don't bounce around randomly. Instead, they're carried along with the air as it flows around fibers, meaning they're likely to get carried past fibers and sneak through even a mask with many layers. But N95 masks have a final trick up their sleeve. They can attract particles of all sizes to them using an electric field. In the presence of an electric field, even neutral particles develop an internal electrical imbalance which attracts them to the source of the field. This is why neutrally charged styrofoam sticks to a cat whose fur has been charged with static electricity. But unlike a cat's fur, an N95 mask's electric field isn't just ordinary static electricity. The fibers are like permanent magnets, but for electricity. Electrets. Just like you can permanently magnetize a piece of iron by putting it in a strong enough magnetic field, you can electritize a piece of plastic to give it a permanent electric field. By electritizing the fibers in an N95 mask, they gain a long-lasting ability to attract particles, which means they capture about 10 times as many particles as regular fibers. That's really good at trapping both large and small airborne particles, and does a reasonably good job at filtering out middle-sized airborne particles. Precisely what fraction of those sneaky medium-sized particles get blocked gives you the number of the mask. If at least 95% of those particles are filtered out, then the mask is rated N95.
Infrared thermometers. Infrared thermometers basics. Infrared thermometers measure temperature from a distance. This distance can be many miles or a fraction of an inch. Infrared thermometers are used in circumstances when other sorts of thermometers are not practical. If an object is very fragile or dangerous to be near. For example, an infrared thermometer is a good way to get a temperature from a safe distance. What infrared thermometers do? Infrared thermometers work based on a phenomenon called black body radiation. Anything at a temperature above absolute zero has molecules inside of it moving around. The higher the temperature, the faster the molecules move. As they move, the molecules emit infrared radiation, a type of electromagnetic radiation below the visible spectrum of light. As they get hotter, they emit more infrared rays and even start to emit visible light. That is why heated metal can glow red or even white. Infrared thermometers detect and measure this radiation. How infrared thermometers work? Infrared light works like visible light. It can be focused, reflected or absorbed. Infrared thermometers usually use a lens to focus infrared light from one object onto a detector called a thermopile. The thermopile absorbs the infrared radiation and turns it into heat. The more infrared energy, the hotter the thermopile gets. This heat is turned into electricity. The electricity is sent to a detector which uses it to determine the temperature of whatever the thermometer is pointed at. The more electricity, the hotter is object. How a temperature gun works. A typical infrared thermometer has following parts: a laser, a converging lens, a thermopile and reference temperature sensor, an amplifier and other electronic components to convert and display the results in numeric values. When you point the temperature gun at something or someone and shoot, a laser is discharged from the thermometer. The laser, however, doesn't have any functional use, nor is it the thing that actually measures the temperature. The laser is only present to help actually pinpoint aim at the object to be measured. Infrared thermometers. Infrared radiation, like visible light, can be reflected, absorbed and concentrated. Thus, infrared radiation emitted by an object or a human is first focused onto the thermopile. Inside the temperature gun, using a converging lens, next is a thermopile, an electronic device that converts thermal energy into electrical energy. How the thermopile is made by stacking several thermocouples in either a series or a parallel configuration. The temperature of a thermopile increases with the amount of radiation incident on it. However, the opposite side of the thermopile stays at a slightly lower temperature, as infrared radiation is not directly incident on it. This difference in temperature leads to the development of a voltage difference, and thus electricity is produced. The electrical reading is then amplified using an amplifier. Ultimately, the electrical reading is passed through a typical data acquisition circuit, and the final temperature reading is displayed on an LED panel in Celsius or Kelvin. An ambient sensor present near the thermopile helps compensate for any radiation entering the temperature gun from an atmosphere itself. An optical chopper is another component that is often incorporated in temperature guns. An electric motor drives the optical chopper and helps the thermopile receive radiation on two different wavelengths. They also consider of various emissivity settings to help check the temperature of different objects. Infrared radiation thermometers are characterized based on their distance to spot ratios, and obviously this number represents the ratio of size of spot area being measured to the distance of the thermometer from the spot. The greater the DS ratio, the greater the range and accuracy of infrared temperature gun applications. A temperature gun finds extensive use in various industries. It is primarily used by firefighters to check for hot spots while extinguishing a fire in manufacturing and electronic industries to monitor machines temperature, the performance of heating, cooling systems, insulating systems, car engines, inspecting electric panels and other temperature sensitive electric parts, etc. An infrared thermometer can also be used to ensure food safety by monitoring heat or a heater oven temperature and food temperature, as well as in agriculture to monitor plant and soil temperature, among others. So this is a video of the based on the working of the infrared thermometers.
Hi, welcome to this tutorial on how to use the infrared non-contact thermometer. The following is an instructional video on how to use the non-contact thermometer. Remove the thermometer from the box and you'll find it in some packaging. Just to confirm the ways that the batteries should go in when you load it into the thermometer. The first battery should go with the pin down. The second battery should go with the top pin up. Activate the device by depressing the trigger for 5 seconds. When taking a temperature sample, lightly depress the trigger, holding the gun in a stable position 3 to 5 centimeters away from the candidate's head. An accurate sample will give you a green reading. When the sample taken is incorrect, it'll indicate low. For demonstration purposes, we had the candidate hold a hot pack up against her head. When a sample is taken and the temperature indicates a fever over 38 degrees, the gun will flash red.
We will discuss about oximeters now. Oximeter, principle of different absorption and light emission. Pulse oximeters use red and infrared light to monitor pulse rate and the oxygenation of a patient's blood. The body scatters and absorbs visible and near infrared wavelengths significantly, so that in order to have a measurable signal, 10 parts of the body must be used. A typical pulse oximeter consists of light-emitting diodes, LEDs, mounted opposite light sensors in a clip that can be attached across a finger or earlobe. As the light produced by the LEDs travels through the body, it is absorbed by an amount that is dependent on its wavelength and the average number of oxygen atoms attached to each hemoglobin molecule. The amount absorbed also fluctuates as the arteries expand and contract in response to each heartbeat allowing the pulse oximeter to determine the pulse rate as well as blood oxygen saturation from the transmitted signal. Pulse rate. A pulse oximeter is a device that consists of a light source mounted opposite a sensor in a clip that can be attached across, for example, a finger. Pulse rate in beat per minute (bpm) can be worked out by timing how quickly the signal fluctuates. Please also refer to the diagrams in the page. Here are a few diagrams for light emitting diodes. We will discuss about light emitting diodes (LEDs) now. Light emitting diodes. Visible and near infrared light has wavelengths of a billionth of a meter, a micrometer, or less. Blue or violet light has wavelengths around 0.4 micrometer. Red light has wavelengths around 0.7 micrometer. Wavelengths beyond 0.7 micrometer are invisible and called infrared. The light source in a pulse oximeter consists of multiple LEDs. Unlike the continuous white light spectrum produced by a light bulb, the spectrum of a pulse oximeter has two distinct lights because the individual LEDs produce light of a single wavelength, either infrared or red. Here is a diagram depicting the blood oxygen saturation. We will discuss about blood oxygen saturation now. Blood oxygen saturation. The amount of light absorbed by the blood depends on the wavelength of the light. For visible wavelengths, blood absorbs blue light more than red. Hence, blood has a red appearance. In pulse oximeters, the ratio of infrared IR to red signals depends on the oxygen saturation, how full of oxygen the blood is. Each of the oxygen-carrying hemoglobin molecules found in red blood cells can carry up to 4 oxygen atoms. Oxygen saturation. For example, 75% saturation corresponds to each hemoglobin molecule, carrying an average of 3 oxygen atoms. Working of oximeter.
How physics tools and methods help fight against COVID-19. There are a lot we don't know about the novel coronavirus and COVID-19. What we know is that we are pulling all our resources together and understand and fight against it ultimately and defeat it. Surface enhanced RAM scattering, fluoroscreen, and atomic force microscopy. These are the few tools which help us to fight against COVID-19. Here, physics plays a major role in understanding and fighting against COVID-19 and helps us to overcome it and defeat it ultimately. Thank you. X-ray crystallography. Physics-based tools and methods helps us an enormous role in understanding and structural feature of the function of vital particles as well as their effects on the body. For example, X-ray crystallography utilizes electromagnetic radiation to produce wavelengths that helps us to generate 3D detailed structure of virus. To help during a pandemic, these techniques are used to provide result very quickly. X-ray crystallography method used to be slow, but with use of automation and fast computation system, the platform and high quality X-rays, it is possible to get the structure very quickly. An example of this fast analysis study of SARS-CoV-2, the high resolution structure of virus main proteins are enzymes that are ultimately enables the replication of the virus. We uploaded the protein bank data bank on February 5th, 2020 by the research team of Shanghai Cyclotron Radiation Facility. It could have been over an years to get the same result 2 decades ago. The structure is helping the researchers to identify and target the search of antiviral drugs that blocks the action of proteins and preventing the virus from replication. Thank you. Psychoelectron microscopy. It's another technique used for obtaining structural information is the psychoelectron microscopy. Psycho-EM is the electronic microscope method applied to samples of cold to very low temperature. A team of researchers at University of Texas at Austin used psycho-EM to resolve the structure of outer spike protein of SARS-CoV-2. It took team only 12 days for harvesting the protein and getting the results submitted to journal Science. The spike you see in the description of SARS-CoV-2 are used to bind the host cell and thus enables the virus to make its way into the cell. The detailed structure of the spike protein is very useful in creating coronavirus vaccine, and the body build immunity if exposed to virus like particles with same external features while being hallowed inside. Thank you. CT scans, the computed tomography imaging technology, widely known as CT scan, uses a narrow beam of X-rays quickly rotated around the patient to produce cross-sectional images or slices of the body. When stacked together, these slices forms a 3D image of patient. Typically, the medical physicists use to CT scan imaging technology to produce an image and videos for cancer screening as well as planned surgeries simply because CT scan provides very detailed information showing the soft tissues, blood vessels, and bone in various parts of the body. CT scan have become the first line of defense in diagnosis of suspected infection. Given the shortage of testing kits, according to the Radiologic Society of North America, healthcare providers uses CT scan to search of opaque spots within the lungs. SARS-CoV-2 attacked the lungs which fails to function properly due to the extent of inflammation. George Washington University Hospital used CT imaging to show the effects of COVID-19 on the lungs of the patient who were otherwise healthy. The video of 3D CT scan released by GWH shows the extent of damage to the lungs caused by coronavirus. So the uh, link of the video is given. You can refer. Thank you. Ventilation: the extensive inflammation that prevents the lungs from being able to supply enough of oxygen to the blood and to remove the carbon dioxide. A ventilation is required to forcefully provide a sufficient level of oxygen in blood. A shortage of ventilation remains critical and in some cases can be different between recovery and death for serious ill patients. Thus, a need to come up with ways of manufacture ventilation quickly, cheaply, and readily. A global team of physicists, engineers, and medical have designed a low-cost and simple mechanical ventilation used off-shelf component. The first function tests were performed on Friday, March 2020. Engineering towards the first prototype units started the next day and construction and the first prototype units began on the Monday. The Department of Physics at UNO is using the Facebook page to keep everyone informed about the current news and updates of physics, particularly as they relate to COVID-19. Students learn about all the physics-related methods and tools to fight against SARS-CoV-2 and COVID-19 through UNO's biomedical physics concentration. This program aims to prepare the next generation of biophysicists, medical physics, and the bioengineer who will ready to knowledge of physics to tackle the next pandemic. It's quite possible they will be able to significantly contribute the structural biophysics to uncover the details of the cause of disease. A medical physics by the diagnosis and treating patient that are biomedical engineering by designing and building the biomedical equipment. So here it's in. Thank you.
These are the materials required for making the pulse oximeter. Here we have the Arduino Uno board. Next is the 16 by 2-inch display for displaying the pulse oximeter readings. So this is the project board for having the components. Following up, next we have the Max 30100 oximeter sensor. And here are the wires for connectivity. So this Arduino Uno board needs to be programmed using Arduino IDE. We will make our own pulse oximeter using the following components. And please note that the video link for making our own pulse oximeter is given in the description. Conclusion: keep yourself and others safe. Do it all. Protect yourself and those around you. Get vaccinated as soon as your turn and follow local guidance on vaccination. Keep physical distance of at least 1 meter from others, even if they don't appear to be sick. Avoid crowds and close contact. Wear a properly fitted mask, and physical distancing is not possible and in poorly ventilated settings. Clean your hands frequently with alcohol-based hand rub or soap and water. Cover your mouth and nose with a bent elbow or tissue while you cough or sneeze. Dispose of used tissues immediately and clean hands regularly. If you develop symptoms or test positive for COVID-19, self-isolate until you recover. Wear a mask properly. To properly wear your mask, make sure your mask covers your nose, mouth, and chin. Clean your hands before you put your mask on, before and after you take it off, and after you touch it at any time. When you take off your mask, store it in a clean plastic bag and every day either wash it if it's a fabric mask or dispose of it in a trash bin if it's a medical mask. Continuing the conclusion, make your environment safer. The risk of getting COVID-19 are higher in crowded and inadequately ventilated spaces where infected people spend long periods of time together in close proximity. Outbreaks have been reported in places where people have gathered, often in crowded indoor settings and where they talk loudly, shout, breathe heavily, or sing, such as restaurants, choir practices, fitness classes, nightclubs, offices, and places of worship. To make your environment as safe as possible, avoid the three C's: spaces that are closed, crowded, or involve close contact. Meet people outside. Outdoor gatherings are safer than indoor ones, particularly if indoor spaces are small and without outdoor air coming in. If you can't avoid crowded or indoor settings, take these precautions. Open a window to increase the amount of natural ventilation when indoors. Wear a mask. See above for more details. Keep good hygiene. By following good respiratory hygiene, you protect the people around you from viruses that cause colds, flu, and COVID 19. To ensure good hygiene, you should regularly and thoroughly clean your hands with either an alcohol based hand rub or soap and water. This eliminates germs that may be on your hands, including viruses. Cover your mouth and nose with your bent elbow or a tissue when you cough or sneeze. Dispose of the used tissue immediately into a closed bin and wash your hands. Clean and disinfect surfaces frequently, especially those which are regularly touched, such as door handles, faucets, and phone screens. With this, we come to the end of the Physics Investigatory Project video. So, on behalf of all my group members, thank you all.